Hi everyone, this is going to be a video walkthrough for question 3 on exam prep week 13. Okay, so we're going to be going over bears and beds, which is a very cool algorithm sorting design problem. Okay, before you guys watch the explanation to the solution, I recommend taking at least like 20 to 30 minutes to try to approach this problem yourself. Okay, so if you guys are watching this and you guys didn't give this problem the time it deserves, like stop watching the video, give more time to think of the solution yourself, and then come back, because this problem is really cool. So it definitely warrants its attention. Okay, so with this big spiel, let's now dive in. Okay, so we have some new hot Cal startup called Air, Bears, and Beds, and it has hired you to create an algorithm. Okay, so I'm gonna skip this introduction and let's go to the problem. Okay, and I have some like bears and beds drawn up for an example later. Okay, so the problem states that we're given a list of bears with unique but unknown sizes, and a list of beds with corresponding but also unknown sizes, not necessarily in the same order. We want to return a list of bears and a list of beds such that the ith bear in our return list has the same size as the ith bed in our return list. Okay, and the big catch with this question is this line right here. Okay, so since we don't know the size of a bed and we don't know the size of a bear, the only information we can possibly get about these bears and beds is by comparing a bear to a bed. Okay, so if we compare a bear to a bed, we get feedback on if that bed is too large, too small, or just right. Okay, and we can also do the same vice versa. So what that means is, suppose we have this list of bears and we have this list of beds. Okay, suppose we choose, let's say we choose this bear, okay, right here, number 30. And we decide to compare bear 30 with bed 40, okay? And 40 denotes the size and 30 also denotes the size, okay? What we would realize, or what we would get out, is that the bear with size 30 is less than the bed of size 40, okay? That's the only information we know, okay? So somehow we have to leverage this knowledge, or this like feedback system, to try to match each bed with its appropriate bear, okay? And it says right here that our algorithm should run in n log n time, and it should say on average. I think I've updated it in the worksheet. And it should be helpful to figure out the naive n squared solution first and then work from there. Okay, so let's try to like start with this naive O of n squared solution and then build our way intuitively to the final answer. Okay, so if you guys like don't want to see the intuition, you guys can just like skip forward in the video, but I think the intuition is kind of nice. So let's go for it. Okay, so my initial idea is, what if we look at each bear in this list of bears? And for each bear, what we're going to do is walk through the list of beds until we find the bed that's equal to the given bear, okay? And then what we'll do is we'll match these two people up, and then we'll move on to the next bear and continue this process of, at each bear, we iterate through the list of beds until we find the bed that's equal, and then we match those two accordingly and move on, okay? So as you guys can probably tell, is that this algorithm will work in n squared time, because for each of the n bears, we do n work in the worst case, okay? So what's like, I don't know, a problem with this algorithm? So the first problem is that we are not using all of the information we get. Okay, so what do I mean by that? Is when we compare the bear 40 to the bed 30, right, using this n squared algorithm, all we're taking out is the idea that it's either equal or not equal, right? That's the only question we're asking. The reason this question isn't enough is that the information we get back from this feedback is we also figure out if it's too large or too small, right? So we're not using this idea of too large or too small in this naive n-squared algorithm, right? So it seems to me that we want to be leveraging this information a bit better than we're doing so right now, okay? And that's like the main problem with this n-squared algorithm. And let's try to build from here to get to the final solution. And the first thing that I want to notice is that our final algorithm should be n log n on average, right? So what algorithms do we know that run in n log n time? Well, some algorithms from class that are n log n are heap sort, right? Merge sort, and quicksort. Okay, so looking at these algorithms, let's try to like draw some ideas. That's like my idea. If we have some sort of algorithm, maybe we can modify it in some way and we can get to a new algorithm that runs in n log n time. Because we know that none of these on their own could solve this problem because it's like not a problem that they're meant to be solved with. Not a problem that these algorithms are meant to solve. Okay, so with this in mind, I think if you look at these three algorithms, the one that makes the most sense for this problem is quicksort. The reason is in quicksort, we often choose a pivot and then we partition around that pivot into three groups. Those too large, too small, and just right, okay? So we can kind of like maybe have some intuition on why we want to go to quicksort. So with going to quicksort, I am going to finally show you guys like the final solution, okay? So I'm gonna try to draw the solution down here, okay? So our final solution is going to be to modify quicksort. Okay, so let's dive into the step to our algorithm, okay? So the first thing we wanna do in quicksort is we choose a pivot. So in our modified quicksort, we're gonna do the same thing. So we're gonna choose a pivot. Well, in quicksort, we usually have one array. Here we have two arrays, right? We have a bunch of bears and a bunch of beds. So let's say that we're gonna choose a pivot bear, though we can also choose a pivot bed, doesn't matter. Okay, and how are we gonna choose that pivot, okay? I'm gonna say randomly. Okay, so why would I choose a pivot randomly? Okay, the reason it's good to choose the pivot randomly is that if we always choose the leftmost item as our pivot, if you guys recall in quicksort, is that our algorithm is more susceptible to the worst case behavior when we have a list that's in sorted order, right? If we have a list that's in sorted order, and we keep choosing the leftmost item as our pivot, we can see that our partitions basically do nothing, okay? So we wanna choose that pivot bear randomly to try to like minimize that worst case risk of choosing a bad pivot. Okay, so after choosing a pivot bear randomly, right, it would make sense that we partition all of the bears about that pivot bear, right? But we can't do that because we can't compare bears to bears. So what we're gonna do instead is we're gonna partition the beds about the pivot bear, okay? And we're gonna do so into three categories. We're gonna partition the beds into those less than, those greater than, and those equal to. Okay, so let's kind of see what I mean by that. Okay, so say that we choose a random pivot and we choose this 30 as the pivot bear. Okay, the next step that our algorithm tells us to do is that we want to partition the beds about this pivot bear. Okay, how we're going to do that is we're going to go through each bed and compare that bed to the pivot bear. Okay, and then we're gonna know if that bed is less than the pivot bear, equal to the pivot bear, or greater than the pivot bear, okay? So using those comparisons, we can partition the beds into these three groups. So let's see what those groups are in this example, okay? So looking at this example, we'll see this first group are the less than beds. Okay, then we see right here, these are the greater than. Okay, and then we see right here, this is the equal. Okay, so what we've done so far is we've partitioned the beds about the bare pivot. Okay, but if you guys recall, the next step in quicksort is to recurse on the less than and recurse on the greater than. But we can't really do that because we don't have all of the bears that are less than, and we don't have the bears that are greater than, right? Because our function, like let's say we have some function called beds and bears, right? This function needs a list of bears and it needs a list of beds, right? So if we want to call a function recursively, we have to give it both a list of bears and a list of beds, okay? So my idea is that after partitioning the beds, let's now partition the bears. Okay, I'm gonna make that step 4. So we're gonna partition the bears about some pivot bed. And the reason I did it as step 4 is because we need to find a pivot bed, right? Should we choose a random one? Well, the problem with choosing a random pivot bed is, let's say we choose 5 as our pivot bed, then our partitions in the bears may be completely different sizes as the partitions in the beds, okay? So this is like, I think the crux of this problem is when we choose this pivot bed, we want to choose the bed that is equal to the pivot bear. So we will choose the equal bed as the pivot bed, okay? And then right here, we're gonna say about the pivot bed, okay? So what do I mean by that? Well, we know that the pivot in this example is bear 30. So our pivot bed should be the bed that is equal to the pivot bear. And the reason for this is now we can partition all of the bears about this pivot bed. This is really, really cool. So notice now that we can compare each bear to this pivot bed and break it into 3 groups, right? Those that are less than, right? And then those that are greater than. And then the one that's equal, okay? So now what we've successfully done, right, is we have found one match and we've partitioned the bears into a group that's less than and the beds into a group that's less than, and we found the bears that are greater than and the bed that is greater than, okay? So what we've successfully done right now is we have matched, right, one bed and one bear, and we've set ourselves up to do a recursive call. Okay, so let's write in those steps. So what we have done is we can match the pivot bear with the pivot bed. Okay, and the reason is that we know that these are equal, so this bear 30 can now sleep in bed 30, right? And if we want to be a bit more rigorous, we can say like, add them to our answer list. Okay, so now our answer list, right? Let's say that it has the bears and the beds, right? We'll have bear 30 and it'll have bed 30. Okay, and then every time we match a bear and bed in the future, we'll add it to this bears and beds list. Okay, but it's not like completely needed. All the intuition is that we want to match a pivot bear with a pivot bed. Okay, so then the last thing we're going to do is we want to recurse okay, on two possibilities. We want to call our function. Let's call our function bears and beds. We'll call it B and B on the less than bears and the less than beds. And then we will also call our function on the greater than bears and greater than beds. Okay, so this is our final solution. The gist, just to reiterate once more, is that we'll choose some pivot bear and we'll choose it randomly to avoid the worst case behavior in quicksort. And then we're going to partition the beds about that pivot bear into 3 groups, those less than, greater than, or equal to. And then we're going to choose the equal bed as the pivot for partitioning the bears, right? And we're going to partition the bears into these same groups, right? The same groups from the previous part. Okay, so then now what we're going to do is we can match that pivot bear with the pivot bed, and then we can recurse, right? And this is exactly how quicksort works. So this is quicksort, right? Okay, that's all for this video. I hope you guys enjoyed it. It's a very cool question. And yeah, good luck for the upcoming final.